Okay, so we're going to start the lecture today. We're going to do a problem here. So really simple. We're going to use this graph. It's a composition graph of tin versus lead. Tin and composition of tin and lead, and basically a tin lead alloy. And the question says that we have a total mass of 2.8 kilograms. And M beta primary is equal to 2.21, and M beta total is equal to 2.53 kilograms. So what we're going to do here is basically so it's basically, let's look at it this way. It's asking for beta, and at a temperature of 180. So that's, we can assume that's just below the eutectic line. So right here, this is the eutectic line. That's the eutectic line. And what we're going to do is basically we're looking for a composition that's between this here, the eutectic point, and the beta, the solubility, the maximum solubility of of lead in tin right here. So the first step is we're going to assume that we're going to assume that CO composition that we're looking for is right in between here. And then next, what we're going to do is, let's take our graph with us. Alrighty, so let's take our graph of this here, and now let's draw that again here. Okay, so first thing we're going to do is we're just above the eutectic line. I'm going to call that the T equals 183 Celsius line. And just above that, we're going to have S and R prime prime, and then we're going to try and find the weight fraction or mass fraction of beta. So what's the mass fraction of beta? That's going to be CO. That's going to be, or actually, you know what? Let's do it first. It's going to S prime over R prime plus S prime. So that's going to be CO minus 61.9 divided by to that point here is 97.8 minus 61.9, and that's going to be equal to it's going to be equal to the fraction of beta. Okay, and that's primary. Okay, so what we're going to do here is find the mass fraction, weight fraction for beta prime. So the way to do that is basically mass of the beta primary divided by mass total will give you basically the fraction, weight fraction. So let's see what we can do here. Okay, we were already given that information back here. So that was 2.21. So 2.21 divided by 2.8, that's going to give you 0.789. And mass fraction of total beta is going to be mass of beta, total beta, divided by mass total. That's going to be 2.53 divided by 2.8. That's going to be equal to 0.9. And that's what we want here. So that's going to be equal to 0.9. You plug that into a calculator or you solve it. Just a little bit of basic arithmetic. Solve for CO. 61.9 minus 97.8 minus 61.9. Solve for it. And 97.8, 61.9. Okay. Oh, so pardon, I just, that was not right. That's not right. Oh, damn it. That's this one here. So that's going to be 0.789 and 0.789. And that's going to be equal to, so we found CO here, CO to be equal to 90.225%. Right on. So let's solve for the fraction of total beta. Total beta. And the way to do that is very simple. What we're going to do is go just below the line. We're just below the line, the T183 line. And what we get here so we're under the line, so just below the line. So we're going to call this S, this is going to be R. So to find beta, we're going to go S over R plus S, and that's going to be CO minus 18.3 divided by 97.8 minus 18.3. And let's solve for CO. Well, that's going to be equal to 0.9. So there you go, that's right. That makes more sense here. So 18.3, 18.3, and let's solve. So we get CO to be 89.85%. That's pretty darn close to 90%. So since these two values, the CO, are equal for each one, then this alloy with this composition of beta primary and beta total is possible. And that's the end for this question. See you later.